Hello, everyone. Heinrich wrote my name down, so now you all know what my name is. I'm a student, a PhD student of Heinrich's, and also of another group, the Computational Social Science group here at ETH. And I am doing a PhD mostly on the intersection of game theory and reinforcement learning. So I'll talk to you a little bit today about things to do with algorithmic pricing and what happens when a lot of algorithms come together in a market and how we might try to think about this. And first off, I'd like to get a sense of what your backgrounds are. You guys are all ETH students, right? I ask because it's also being done with the UZH students. And who has a computer science background here and who's familiar with reinforcement learning? All right, many of you. And what about your other backgrounds? Any physicists in the room? Or yeah, nice. Engineers? Okay. All right, well, hopefully today it'll be somewhat self-explanatory for all of you. And I've also been getting really good at using AI. So I've been doing my best to get Gemini to produce something interesting, and before I was even able to finish my query, it had already produced this brilliant collection of things. I suppose you've studied all of these at this point in this course, but I definitely missed a bunch of important references from that. But pressing it a little bit harder, I was able to get this image out of it, which was a little bit more in the direction of what I was hoping to convey, and it's somewhat a stylized representation of what we have going on nowadays in a market. Many people, perhaps on opposite sides, firms, companies, platforms, sitting behind computers, making decisions, programming algorithms, and just a barrage of information, of digital bits thrown at people, at a consumer group, and this constant feedback between this large group of people and a lot of sort of algorithmic decisions. And so we might naturally ask ourselves, what happens to our markets when this is the dynamic? And the outline for today will be motivating this study a little bit more with some examples you might be familiar with. Then we'll look at a simple model of competition to get an understanding of what we actually might expect in a market. We will then look at some algorithmic pricing, as would be done with Q-learning. So that's the method that we'll be looking at today, and I suppose several of you have already encountered this before, and others will not have, so I hope by the end of today, in the very least, to have shown you that it's very simple and but quite apt for looking at certain cases like these. And finally, we'll look at a sort of a broader outlook and a small discussion about algorithmic pricing in general. So I assume this doesn't look anything new. An Amazon marketplace page. You've seen many things like these. The items on screen aren't particularly important, but we are often confronted on the web with these large tableaus, these large menus of items, each with their own price. You can almost infinitely sort of follow trails, and everything is priced. Everything is always priced. There's always a price. Now, how do we get these prices? Where do these prices come from? Of course, you could say, yes, supply and demand. Yes, okay, that's all nice theory, but how are these prices actually set? Amazon is huge. Amazon also produces all kinds of its own products. It's actually a producer. It's not just a retailer. And it competes with all of the clients that it has on its own platform. So somebody will come along, an independent party, and be like, I want to sell a water bottle or soap or whatever it is. And Amazon will see that and see the prices that they set for their items, and they'll decide, you know what, we can do better. We'll produce water bottle or soap, and we'll price it too. And you know what? We can also price it more competitively than the other vendor. So I'd like to show you briefly this video. This comes from the team at Amazon that actually manages pricing.
We price every single Amazon-owned piece of inventory on the Amazon websites globally. So every single thing you ever think of buying that's physical and shipped and sold by Amazon was priced by my team.
In order to earn the customer trust, we would expect the customer to be able to just come to Amazon and see that we have the lowest price, so they don't even have to try to go to other places.
We are a very technical company, and we have built, very vast, robust, scalable system that does many different things that all of which contribute to the price, and they react in close to real time.
We have to price millions of these items. So the scaling is one of the major things that we have to think about all the time.
We don't just sell one type of product. We sell everything. So every sort of industry's nuances have to be accounted for.
Yeah, it's very important to have as many things become automated as possible to reduce the cost of the people that have to work on, and the people that we hire can focus on something else that could be even more important.
A lot of our competitive advantage in pricing is coming from the technical frameworks that we've set in place. So people who have that unique blend of technology and business and who are comfortable in both worlds would find this role very challenging and exciting.
Okay, this is not an endorsement to go work for Amazon, but it's probably an interesting position considering the scale of what they're doing. We price everything. They say millions and millions of items globally. That's a lot of stuff. Also, if at any point you feel like interjecting, any point, questions, feel free to interrupt me. So the scale of their operation is far outside the scope of what we can investigate in an academic setting. But this is happening live, and it's something that we should be aware of. So another example would be Booking.com. I'm sure you're also familiar with this view, or Airbnb, or Expedia, or any other kind of similar platform. They also have prices for all of their hotels. In fact, they have to price not just for the single query that you are asking in that moment, right? I might be searching for a hotel for tomorrow night, today. That is one kind of query. But what about a hotel for in 10 days for one night today? But what if I search for it tomorrow? I mean, all these things are variable. All these things are determined to some extent on the spot. There are some heuristics that people set, and but then these prices are determined on the spot. And to be perfectly clear, we have no idea how they determine these prices, because it's proprietary software to a large extent, or perhaps because it's the individual hotel decisions. But we also have some indication that it's not just the individual hotels setting these prices, because there's this booking suite tool, a rate manager, which is actually really hard to find any information about, understandably also because it's proprietary software, that Booking has that allows it to price for its customers. So a hotel comes onto the Booking website, it has a history of a few years, and Booking knows the demand that it has achieved over those few years, it knows its competitors' demand, it knows so much more. Basically, it is the marketplace. And then it provides a service to the hotels. It tells them, let me recommend you a price. In fact, click this button and allow me to set the prices for you. I guarantee you increased revenue and profitability. That sounds great. Why wouldn't you want increased revenue and profitability? But does that make sense? I mean, can you guarantee increased revenue and profitability to all of your customers? Or, I mean, I guess perhaps you can, but what consequence does that have on the market? What are you actually doing there? So I've actually been looking a little bit at some data from Booking.com in a very preliminary investigation, kind of following some of my research, and this is just an example of 2 months and 10 hotels in Times Square. So these are all in a similar area, and you might reasonably expect that they should actually be influencing each other. You know, perhaps they aren't perfect competitors because actually the hotels are, I mean, even though they're all 5-star hotels, perhaps the hotels are, you know, they are differentiated and they have a particular client base, but nonetheless, you might expect that they would influence each other. And the way I made these queries was by asking Booking.com for the price for one night tomorrow today. So sort of at every hour, you ask for the price for one night tomorrow. Not really clear if this is the best way to query, but it was just one way, and this is just very stylized data. But we can look a little bit closer, for example, just 2 hotels, and I mean, we clearly see that there's some oscillations in the data. It's hard to know why these oscillations are there. There are many contributing factors. There are clearly weekends in between. There's also maybe some seasonal trend. I mean, New York, perhaps in early March, is still really cold and not very hospitable, but gradually as spring comes along, it becomes a nicer and nicer place to be. This is just pure speculation. We don't really know why these prices change. But there's clearly a lot of fluctuation, a lot of variability. There are even some rather repeatable patterns. These tiny kinks that happen, you know, over and over again. Turns out they align with midnight. So, to some extent, probably an artifact of the query that I was making. But still, if I was to book the hotel at this hour on that day, I would actually get a, you know, maybe like $40 discount and that's repeatable. You might think this is not very efficient. It's exploitable. But we might actually think that this is, from the perspective of the hotels, it might actually turn out to benefit them tremendously. Of course, if your platform, if Booking allows you to price your hotel based on the information that it also has of your competitor, and it guarantees you increased profits, perhaps it's coordinating you with your competitor. Perhaps it's trying to make sure that you guys are both equally happy. You know, and this is all just speculation, right? So like, don't take my word for it. We have no idea what Booking is doing. But to get a better idea of what we might actually expect in a market, we need to have a model of this kind of price competition. And one such model is a Bertrand duopoly. So this is going to be a big simplification of what you might reasonably expect to happen in a market, but I hope to convey to you why it might be useful to get an understanding of what we might expect. So a Bertrand duopoly is a 2-player game. It's symmetric, so both sides have the exact same setup. They have the same actions that they can take, and they have the same reward, the same payoff. So we have 2 sellers, in which case we'll stick with the hotel analogy. There's 2 hotels, and they have to price a room. So they have to set a price. That's all they have to pick. And for the sake of simplicity, we'll assume that they have a price range from, you know, just 1 to 10, for example. Yeah. Then, based on the price that they set, they will attract a certain amount of demand to their room. If they set the same price, they will split the demand evenly. If they set different prices, the lower price will get all the demand. So in economic terms, this is very price inelastic. So the consumers are purely motivated by the price, right? So if a lower price is always more attractive. This is one of the core assumptions. And again, of course, this is a little bit simplistic. We know that there are situations where this is not quite the case, but it shows us the extreme case. So, right, then finally their actual payoff will be the price that they achieve times the demand, and there's some marginal cost, but we can somewhat forget about that. So, based on this setup, what might we expect to happen in a duopoly like this? So, if we just ask two hotels to set a price, what prices should they pick?
Like if you have like a short-term vision only, like you would like try to like always slightly undercut your like other hotel because it will make all the profit as long as you have rooms, but this will lead to like the profit conversion to zero. So if booking is like the prices, they can like coordinate and keep high prices. Kind of like, yeah, but that's
right.
not legal. But
Indeed, yeah. Yeah, so the best response to the opposite hotel's price would be to undercut them. Right? That's at least that's one reasonable way to think about strategizing. Absolutely. And as you say, if we kind of undercut each other over and over and over again, eventually we get to the minimum price that we are willing to charge. And that is actually what we would call the Nash equilibrium. Because if we're both setting the minimum price, no hotel wants to raise their price. Raising your price will incur a loss because you suddenly get no demand. So the case where both firms set the minimum price is our Nash equilibrium of the Bertrand duopoly. And this is a simple model of price competition, and it's actually used to illustrate why in a competitive market, it is enough for just two players that are competing on price to get this sort of equilibrium price, this competitive equilibrium, which is actually good for consumers. This is one of the arguments for why we want competition in the market, one of the arguments for markets. I mean, to some extent, we know that competition increases with the number of players, or that's just an intuitive idea. The more competition you have, the better welfare for the market you will have. That's just one stylized idea. So if anything, the Bertrand duopoly also shows, surprisingly, that it might be enough to have just two. But in any case, this is just a stylized model, but indeed, that is one of the outcomes that we could expect. And there's a few other outcomes that people typically reason with in this case. So the first one, which we just discussed, is the perfect competition, where the price is driven to the minimum. Another one is actually monopoly pricing. And so this, of course, makes more sense to think about if you just had one hotel. If you just have one hotel, it doesn't have an opponent to undercut. So it can basically set the price as high as it is able to attract demand, which are able to maximize its profits. So it's still not, you can't set a ridiculously high price because at some point you'll just attract no customers, but you can sort of raise it to the point where you are able to maximize your profit. And the monopoly price is understandably much higher than the competitive price. But it is possible to achieve this kind of monopoly price even if you have more than one hotel. Of course, you might just agree with your neighbor. Let's set this price for our rooms and forget about competing. And as you've already suggested, that's illegal. But one might also achieve this kind of outcome without communicating. You might implicitly understand that lowering your price sends a signal to your opponent that you're kind of punishing them. You're sort of signaling that you want to compete. And you know that if you compete with them, they'll compete with you. So in a way, you know what the consequences of competition are, and you might choose not to go down that road And you might signal that you aren't going down the competitive route by not undercutting your opponent. Now, your opponent, on the other hand, might be looking at what you're doing, looking at your prices, and see you not undercutting their price, and take that as a signal that you are choosing not to compete with them. Of course, their best response in that situation, depending on the way you think about it, might be to compete with you. Like, this guy's cooperating with me, I'm just going to knock him out. But you also recognize that perhaps there's a long-term, long-standing relationship. You actually kind of like the guy. You don't want to punish him, and so maybe you'll play this sort of cooperative game without actually communicating. So it is possible to maintain this kind of coordination, but an economist would argue that this is just unstable and unlikely, and depends on many other factors that aren't rational economic choices. And to some extent, we also just can't verify this. We can't look into the mind of the hotel owner and understand what they're doing. So it's somewhat unverifiable. But if at any point I was to communicate with my opponent and there was a trace of this communication, suddenly there might be reason for concern. At least that is an explicit attempt to coordinate. All right, then the final focal solution that people also reason with are Edgeworth cycles. And these are sort of sequential undercutting processes. Somewhat what we just discussed earlier, where you have an opponent undercutting the other, undercutting the other, undercutting the other. This is sort of like a stepwise decrease towards the competitive equilibrium. But if both of us are just reacting purely to our opponent's last price, we might get another kind of solution. Because when we're both at the competitive minimum price, it now suddenly becomes quite appealing for one of us to drastically raise the price. And you might wonder that doesn't make much sense because you'd lose your profits. But when I drastically raise my price, now my opponent's best response is to undercut me, which drastically raises theirs, which gives them higher profits, which allows us to reinitiate a sequence of undercutting, which on average gives us much higher profits. So this is just another sort of solution that people reason with in the context of the Bertrand duopoly. So we can see again that, as is often the case in economics and economic games, there aren't these. I mean, the solutions are many, and they depend on our assumptions. This is part of the difficulty of doing economics. And indeed, if we have these two hotels, and we find them to communicate such that they're able to coordinate and achieve, say, a monopoly price. This is collusion. This is what we call collusion. And in international law, in US law, in European law, this is illegal. And it's really defined as this explicit act of communication between two between two parties, between two parties that should be competing. And when we instead have this supra-competitive pricing, which is actually not due to communication, but is instead due to some kind of implicit understanding that you shouldn't punish your opponent because they'll punish you back. We think of this as a tacit kind of collusion. There's no communication, it's tacit. And this is actually not illegal. But the reason why it's not illegal isn't because it's a desirable kind of coordination between two parties that should be competing, but it's rather because it's really hard to determine that that's what they're doing. It's almost impossible to measure it. I mean, it might even be impossible to measure it. So we are constrained by what we're actually able to detect in the real world. And so this motivates our research questions for the investigations that I've been doing, or even more broadly speaking, when people think about algorithms in markets, one of the concerns is, do these algorithms make collusion easier, right? Is it now suddenly much easier to collude with your opponents, even though you should be competing? And secondly, what does collusion look like? What does algorithmic collusion look like? And finally, can we distinguish the tacit kind of collusion from the illegal kind where you're actually explicitly communicating in this algorithmic setting? And there has been quite a lot of work that has looked at this in economic context, specifically studying the Bertrand duopoly. And the basic setup is using Q-learning, which I will introduce in a moment. And they find all kinds of different results. So one paper finds that Q-learners achieve these kinds of super-competitive focal prices. So that's just a high price, which is quite stable and steady, and is much higher than the minimum price. And they find that when they take two Q-learners and they train them together, that they can achieve these kinds of high prices. On the other hand, we also get results that show that they're also able to achieve those Edgeworth cycles that we mentioned earlier, where they undercut each other, and then they jump up, and then they undercut each other again. So in the literature, these are two rather famous results, and there are other slight variations of these. But in our setup, we actually found their assumptions to be somewhat lacking. And to understand a little bit why, we will dive a little bit into Q-learning. Please.
Do you model consumers and demand in this case?
They are modeled very simply as taking the lowest price, and if the prices are equal, they...
Demand by type, because in Edgeworth cycle, I think it's high, right?
Right, so the demand is inversely proportional to the price. So when the price is higher, the demand is lower. Linearly, that's how it's modeled, yeah. So indeed, higher prices, fewer consumers. So Q-learning is a very simple learning method. It's one of the most fundamental reinforcement learning methods where we learn by interacting with an environment. And so it has a Q table. And in the case of our simple game, our opponents will be learning, based on my opponent's price, what price should I set? So for this, you just get a grid, which identifies each possible situation where you have an opponent price and the price that you might respond with. And over time, you learn a value for that action. And you learn the value for that action by repeatedly trying all the possible scenarios. So there are three important learning parameters. The learning rate, which tells us how quickly do I learn, how much do I incorporate the newest piece of information into my beliefs. The exploration rate, which tells us how often do I explore. So as I am picking prices against the price of my opponent, how often do I pick a price which I don't believe to be the best one to learn more about things that I haven't tried much yet? And the final one is the discount factor, which tells us how much we care about the present reward versus how much we care about the future reward. Because of course, actions that I take in the present might influence things that I'm able to do in the future. So how much do I care about the future and how much do I care about the present? And as these Q-learners will be playing and learning this game against each other, they have to pick prices somehow. And they do that with a policy, which is epsilon greedy, which means that with a probability 1 minus epsilon, they will pick the price which they believe to be the best price against their opponent, given the price that they set. So with a probability 1 minus epsilon, you do what you think is best based on what you've learned. So it might not actually be what is best, but it's sort of It's your current estimate of what is best. And with a probability epsilon, you do something random. So with a probability epsilon, you explore. So epsilon is this kind of like the randomness, it's somewhat the noise, it's the exploration rate. Then we have the updating rule for the Q values. So each cell in our table is a Q value, which maps the opponent's price and a price that we may set. And whenever we observe an opponent's price and play a certain price in response, we're going to observe a profit, a reward. And we use that reward to update our estimate for the value of playing that price given our opponent's price. And we do that with this rule where our learning rate alpha governs how quickly or how much of this new information we integrate to update our past belief. And the parameter gamma weights this term here, which is the sort of a maximum over the next price of the opponent and the next maximum price that I may pick. So it tries to incorporate something about the future. Given that my opponent played this price, and I now observe this new price from my opponent, what am I able to do? Like, given this new state that we're in, what am I maximally able to do? And I incorporate that into the estimate of the action that I just took. So I don't know if that sounded complicated or not, but this is actually just a very simple method for learning. I mean, naively, these two agents are trying everything that they possibly can against each other with some action policy, with some rule which governs how they pick their actions, and over time they learn. And so I mentioned earlier that the previous literature that we discussed made some assumptions that were odd, perhaps, or at least that we try to expand on. So the setup that they investigated, and perhaps this is familiar to those of you that are computer scientists and have looked at reinforcement learning before, was basically to take these two Q learners and start them with a very high exploration rate. Then they would train them against each other. So they would start picking actions, they would see profits, they would start picking actions, and gradually they would decay these exploration rates over a long period of time to 0 to try to get them to converge to something. And then they would analyze what their final converged behavior was. What had they learned in the end from their interactions with each other? And they would find that they learned these collusive outcomes, these steady high prices, and in a slightly different setup, these Edgeworth cycles. So this is sort of the training testing, the classic training testing split that we see in all kinds of machine learning. And it allows one, in a way, to explore freely all the possible outcomes, and then to just deploy what you've learned, right? And where we think this is somewhat odd is in assuming that you are able to freely train against your opponent. I mean, surely if I have an algorithm that is pricing things in the real world, that has an effect on my profits. And if I'm doing in-house training, I'm most likely not able to train against my opponent's algorithm. So we decided to take a slightly different setup and study instead the continual learning of these learners. So looking at the learning dynamics, we take the Q learners, we pit them against each other, but then we're actually interested in the average profits that they achieve over time rather than the final learned behavior and the kind of collusive behavior that they achieve at the very end. And if we think in terms of regret, which is, I don't know how many of you are familiar with the notion of regret. Well, this is a common way of talking about objectives in reinforcement learning. But the simple regret would be the case where you basically have your entire learning period to try all possible outcomes, and then over that entire learning period, you're able to pick the best choice and evaluate your sort of best learned choice as your performance. That would be the simple regret. You kind of get free exploration all the way in between, and then you just evaluate it at the very end. Kind of like you may perhaps like maybe studying for an exam. You know, you can freely explore during the course, and then you just get evaluated at the very end. Versus complete regret, where complete regret actually takes into account all the steps along the way. Sort of what are your performances along the way, and this is what you care about. You care about the stepwise performances, and that's what we will be looking at in this setup. And to try to analyze this, we come up with the abstraction of the metagame. So by the metagame, we mean the game that the algorithm designers play against each other. So it's not just two Q-learners that might do some collusive behavior, and all of a sudden we have to be worried that AI is going to ruin our markets. What we're suggesting is that it's actually a designer question, where you have two designers that pick the learning parameters for their algorithm, and then these two algorithms compete with each other, and a certain outcome comes out. So the metagame we set up as these Q-learning algorithm designers, two Q-learning algorithm designers, though it could be more. Their actions are the choice of three learning parameters, and we discretize these learning parameters so that we actually have a finite action set. And the payoffs will be their average profit in a repeated game. So these Q-learners come together, they play the Bertrand's duopoly against each other for, say, 100,000 rounds. And then we take the average over all of their profits, and that will be, for both of the algorithm designers, their payoff. This is how well you did. And you could reasonably expect that an algorithm designer wants to maximize that average of all their payoffs, or the sum of all their payoffs. And so this is the incentive structure that we analyze. And because we have three parameters, the learning rate, the exploration rate, and the discount factor, we can visualize them in a cube. And a single parameterization is just a point in the cube. And so at any point in time, we would have 2 points in this cube, or sort of two parameterizations. Then, because we will be evaluating for each of these points what the average profits are, an arrow in this space we can think of as a best response. So we will think of a best response as, given that my opponent picks this set of parameters, which set of parameters would I like to pick? So what is my best response in this space? What parameter set would I ideally like to pick against my opponent with those parameters? That's what we think of as a best response. So to evaluate this space and the incentives in this space, what we had to do was effectively try all parameters, and it's a relatively simple process, but a very intensive computational study. It took, I think, about 6 days or 7 days running on the Euler cluster to calculate all these things. Of course, had to repeat many times to average out and make sure that we have the right results. And things always go wrong in the process. And I think the most CPUs I was able to request was 960, which is a fair amount, but of course, if you're able to request more, you can do it in less time. Yeah, I think it was 6 or 7 days that it took to run these experiments. But surely there's ways to optimize the code. So if any of you guys feel like throwing yourselves at it, you can let me know. And just to recall ourselves what the research questions were and some results for them, the first one we're looking at is, do algorithms make this kind of collusion easier? In this new setup where we are looking at the average payoffs rather than the limit payoffs. And first answer to this question would be that yes, we find a lot of parameter combinations in our space which are collusive. In fact, it seems like a majority of the combinations of parameters in this space are collusive. There's a limitation with this figure. We are only able to see the symmetric parameter combinations. Right? Each point in this space is one combination of parameters. But we have 2 players, so we can have two parameters at a given point in time. So given that we're only visualizing single points, we're looking at the cases where both players have the same parameters in this figure. But still, when both players have the same parameters, we have a lot of outcomes which are very collusive. And the only outcomes which were really competitive and actually had a minimum price really close to 0 were the cases where the exploration rate is really low, is 0, right? This surface is very low. Now, we're actually interested to understand not just how collusive are parameter combinations, but we're interested to understand what is, given my parameter's opponents, what is my best response? So we're interested in competition in this game, because that's truly what we should evaluate algorithm designers on. Are you competing with your opponent's algorithm, or are you actually coordinating with them? And so for that, we need to look at the best responses in this space, where the circles are our best responses. I've now removed almost all arrows and just kept the parameter combinations that are a best response to at least one other parameter combination. And we find that there's actually a unique equilibrium to which eventually all the best responses point to. And it has the sort of the largest circle around it, because the size of these circles counts how many the number of best responses that point to that particular set of parameters. And this equilibrium has a particular set of parameters. I think alpha is about 0.1, epsilon is about 0.25, and gamma is about 0.2. And the reason why I don't focus too much on what the exact values of these parameters are is that it depends to some extent on our discretization. And I think really the insight here isn't too much that what the specific parameters of the equilibriums are, but rather that there is a unique equilibrium that is pure and symmetric. Right, so actually, yes, it's also symmetric. So both players want to set the same parameters. And so this is the Nash equilibrium of this metagame, which would be what we expect if these algorithm designers are actively competing with each other, which is what we would want in a market. On the other hand, we can also look at another set of solutions, which is called the Pareto front, which we could think of as a case where these algorithm designers are actually collaborating with each other. Or what if they take their opponent's payoff into account? What if they will only deviate to other parameters if it doesn't hurt their opponent? So this is some kind of cooperative behavior. And what we find here is that all the Pareto front solutions are actually asymmetric. So we represent these as lines between 2 points. So these asymmetric combinations typically have one algorithm acting quite randomly. For example, we see that many of them are clustered in that upper corner, which has an exploration rate which is very high. One player acting rather randomly, and the other player acting sort of much more selfishly, but together they're able to achieve much higher average profits than in the competitive case. And so what do these dynamics actually look like if we look more closely at the individual cases? So for the competitive outcome, we find that these algorithms are mostly pricing at their minimum price. And it's very noisy though. So they're occasionally setting higher prices, kind of like exploring the space. But really what they've learned to do is price at their minimum price of 1. There is also a price of 0 here, which they occasionally test. And that is because there is some noise in their policy. But at a price of 0, clearly they are not going to be making any profit. And so we can think of that as sort of just the 0 profit case. But 1 ends up being what they set, which gives them a small amount of profit. But this is competitive behavior. This looks like competitive behavior, even though it's very noisy. And I guess you might wonder, why is it so noisy? Like wouldn't one player rather always set a price of 1 and thus beat the other player, right? If we just look at this snapshot, that's a fair question. And that actually brings us to this notion of regret that I mentioned earlier. So if we, given this pricing strategy, this pricing outcome, you might look back at this result and think, was there a single price that if I had set throughout the entire play, I would have been better off? And in this case, there is, right? You could just set a price of 1 always, and then you would be able to exploit your opponent every time they deviate, and you would be better off. But that's actually not what we're able to look at here, because what we are picking isn't our sort of specific pricing strategy. We're picking a Q-learning algorithm. We are picking an algorithm which is set to explore and compete against another algorithm, and now we're just able to observe the result. But if we had picked an algorithm that was less random, if we had lowered our exploration rate, we would have achieved very different learning outcomes, which, based on our analysis, would actually have allowed our opponent to pick a different set of parameters which would benefit them more. So this is the behavior that we would expect at the equilibrium, if the agents are actually picking the parameters of the metagame which maximize their profits. So still, it's surprising that you get this kind of noisy collusion. And on the other hand, if we look at a solution from the Pareto front, where they might instead be coordinating and collaborating, we find some competitive pricing, but we also find them able to set higher prices and to coordinate them on them in a somewhat intermittent fashion. So this understandably achieves a much higher average profit over time, and is why it's beneficial for why we find these solutions on the Pareto front. And we can also see that there are some sort of the appearance of some cycles where a best response from one agent leads to some temporary cyclical behavior, but it's still very noisy. So nothing like those very clean Edgeworth cycles that we have on the one hand in theory and on the other as some experimental verification when these Q-learners are actually forced to converge. Here we're looking at their learning dynamics, their noisy learning dynamics, and for this reason we find much noisier pricing patterns, which have the suggestion of a cycle. And so then for the final question, can we actually distinguish the kind of tacit collusion from the kind of illegal collusion? So again, the collusion that we get in the Nash equilibrium of the metagame, where these algorithm designers are actually competing with each other, which leads to this noisy competitive pricing behavior, that could be, that is tacit. What do I mean by tacit? If purely by competing to maximize their average profits, the algorithm designers could reach this equilibrium. Does that make sense? So they wouldn't need to coordinate with one another. All they have to do is maximize their average profit, and given enough time to try things against their opponent, they could reach this equilibrium. And so they don't need to communicate, and that's why we could think of it as a tacit outcome. But as we saw, it's competitive, but there's still a small amount of profit, so it's kind of like a tacit collusion. And in that case, this is the best response graph that we get during their learning, or just a snapshot of a best response graph, where each of these nodes is a pair of prices. So there's 2 prices. And the arrows represent the best, the next pair of prices if both players pick the price that they believe to be best in that case, right? So I hope you're able to see something from here, but here we have a price 2 and a price 4 for player 1 and player 2, and if they both pick the price which they have learned to be best based on their Q table, if they just argmax their Q table based on their opponent's price, next combination is price 3-1. If they argmax again, next combination is price 1-1, and if they keep argmaxing here, they just end up at 1-1. So this is sort of we find them stuck in this pair of prices. Whereas in the Pareto front case, so where actually there's some kind of coordinated collusion. They're caring about each other's profits, and perhaps they are doing so by coordinating with each other. We find a different kind of structure, and particularly focusing on what we see in the upper left-hand corner, we find that they can oscillate between pairs of prices which are higher than the competitive prices. Right, up in the corner, they're oscillating between 2-2 and 3-2, and they sort of go back and forth. And we can notice that they're oscillating between a price of 2-2 and a price of 3-2, where it seems like the player which always sets a price of 2 is benefiting, right? Here they split the demand, here it gets the whole demand. So in these asymmetric Pareto front combinations, which are able to maximize the average profits, one of the players is losing out compared to the other, but on average is still achieving a good profit. So this is that kind of asymmetric behavior that we see coming up for those outcomes. And it seems from relatively simple statistical tests that we are able to distinguish this behavior just by looking at the prices. So what we did here was simulating a few different runs, some of them with the parameters that were at the meta-Nash equilibrium, some of them with parameters that were at the Pareto, on the Pareto front. And we find that if we compare two pricing dynamics that were generated from the meta-Nash equilibrium, that we're able to statistically determine that they look the same. Whereas if we compare that Nash pricing behavior to the Pareto pricing behavior, we can statistically find them to be different. Interestingly enough, if we compare two Pareto outcomes, we also find them to be statistically different. So it seems like we're not really able to distinguish between Pareto outcomes, but the Nash, the meta-Nash parameterizations stand out as different to others. But this is a very simple test. It's not something that we could claim to be the case for real-world data, like the booking data that we saw earlier, for example. But in the very least, there is some indication that perhaps competitive dynamics between algorithms might actually be detectable. And this is really necessary for regulators. It's necessary to know if we can detect them or not. Because if we can't detect them, well, we need to come up with a different way to either regulate the use of algorithms or impose constraints on companies, change market structures. I mean, who knows? And based on our findings, we also propose that a checklist of items that we might expect to be useful to actually detect whether this kind of collusion is happening, based on the fact that we know that the equilibrium, this meta-Nash equilibrium, in this simple case, is symmetric, then we expect that the pricing behavior of both of the players should be similar. And based on the fact that we also know that the meta-Nash equilibrium is noisy, we also expect the pricing dynamics at such an equilibrium to be noisy. If you find very clean pricing behavior and you know it's algorithms setting these prices, that might be a little bit suspicious. Unless they're setting an incredibly low price, which beyond reasonable doubt is incredibly competitive. But if prices are not obviously low and very stable, we would say that might be reason for suspicion. And of course, if we find the average pricing dynamics to be really high, that is also reason for suspicion. But the problem with this is that we tend not to know what a high price really is. We don't, I mean, of course, in our stylized model, we know exactly what the minimum price is, and we also know what the maximum price is. But in the real world, how do we know what the minimum price is? In some cases, you could determine it if you're able to know exactly what it costs a company to produce a good or provide a service. Then you could say that that marginal cost of producing an extra good should be your minimum price, because you aren't willing to go any lower than that because you'll be making a loss. But at that minimum marginal cost, you'll be covering all your costs. But in practice, it's often even difficult for the producer to determine its marginal cost, and it's certainly not information that they give out to other market participants. So it's really challenging to determine what a true minimum price is. And this is part of the issue, part of the challenge with investigating this kind of algorithmic pricing behavior. How can you just look at a price pattern and tell how it was generated? And then can you tell if the participants were actually trying to compete with each other? So as a summary of the kind of insights that we hope to have uncovered in this work, we have that algorithms do make collusion easier, because now it's somewhat as simple as taking some algorithms, configuring them in the right way, and setting them out into the market. Right? It's very easy to collude with your opponent. But if you're actually competing, we find that you set somewhat competitive prices with your algorithm. And then we find that this kind of collusion, we would expect it to be noisy. And we would expect it to be noisy because if you're actively learning in the market against your opponent, you need to explore. to learn about certain outcomes, and this exploration would create noise. And in fact, we also find that it is beneficial to both parties to have noise, and that it is better for their profits, and it allows them to get not a slightly above zero profit. And then finally, it seems that we can distinguish statistically from the meta-Nash case and the Pareto collusion in our model. Of course, this is just for our model and assuming that we're able to freely generate this kind of data, but hopefully that's somewhat an interesting avenue of investigation for real-world data. Okay, do you have any questions so far? This concludes the more results heavy and technical part of the presentation.
So you've used Q-learning mostly for that. Have you looked into whether it generalizes to other reinforcement learning algorithms, like deep reinforcement learning or something?
So we have not tested deep reinforcement learning, but others have. But no, so that is definitely one of the interesting avenues of future work would be to look at more other and more varied algorithms. I don't necessarily know if making the algorithm itself more complicated, right? I mean, a deep neural network is going to be estimating. I mean, if it's playing the same game, you really don't need a deep neural network. But right, if you're looking at a much more complicated context where you have a lot more data that these algorithms are integrating, then you might actually need this sort of estimation. So, short answer, no, but definitely worth looking into. There are some papers that look at deep Q-learning specifically in markets, and they also test more players. And they actually find similar results that they can get collusion. That as you get more Q-learners, more deep Q-learners, that this also does tend to decrease collusion, which is also a common prediction from markets. But so one of the downsides of testing a more complicated algorithm is that you end up having much longer computational times, and this makes it less feasible to search the space of algorithm design, to search the hyperparameter space. But there's some indication based on our analysis that perhaps you don't need to search the whole hyperparameter space to actually find the equilibrium, because it seems like we have a pure symmetric equilibrium. So I think there's some good indication that it might be worth, that you can look at much more complicated algorithms and still find the equilibria efficiently.
Another question just about the modeling. Maybe I missed the part or so, but how do you model the price, or not the price, but how much wealth one this competitor has? Is there a cap on this, or do they have to give something away and pay really, or not?
Yeah, no. So they don't have to give anything away. So they, the competitors, we only assume that they have a good that they can price. They pick a price, and based on this price, they get a certain profit.
Yeah, they just get the profit,
And they just get the profit, and then they repeat the game.
But so you would say, what I see there, doesn't this mean you can't model like the monopoly tendency of the market? Like if they can't die essentially, one of these competitors, they can't just be eaten by the other.
Yeah, indeed. This is not trying to model the survival of one or the other company. It's just trying to look at price competition. Yeah, it's one of the the Bertrand duopoly is really explicitly created to show the effects of price competition. So if you have two reasonable competitors and you know, in a slice of time when they might be competing with each other, how might they be thinking about setting their prices? So I think what you're thinking about is not really apt to like model with the Bertrand duopoly, but there are definitely other things that could.
How is that different to collusion? Because one hotel can always just look at the other hotels.
Sure.
Or track the price.
Yeah, that's a nice question.
Or if the supermarket sets prices, another person can visit this other supermarket and just
Sure.
see what prices they're doing.
Yeah.
And so if the information is already out there for the public,
Yeah.
what is there to collude?
That's a very interesting point. Indeed, prices are a form of communication, but it's a private or sensitive form of communication, right? So if you tell me your price, and I can see your price, what's my best response to compete with you? To make it lower, right? And then your sort of best response would be to make it lower in return, right? So prices are a form of communication. I agree with you, but they're sort of the allowed form of communication. It's what the economy is designed around, and they kind of subsume a lot of information into a single value, and we want. I mean, there might be situations where you don't know your competitor's price, right? But based on the fact that we assume the existence of a market and the fact that a consumer would need to access the goods that you are pricing, prices are public information. Like, we just tend to assume that prices are public information. And what theory shows us is that that is beneficial for the market, or not always, but that tends to lead to beneficial effects if we know each other's prices, because then we will compete. If I don't know your price, I can't compete with you.
Okay, so when would it become collusion? For example, if you have a supermarket and another supermarket, one
Okay.
supermarket will always check the other supermarket's prices. That's not collusion, that's just checking prices.
Yeah.
And always covering.
Yeah.
At what point?
Right.
What
So
would become actual collusion?
it would become collusion if I run over to the supermarket, check their price, and then I realize that they've lowered their price compared to our good, and then I talk to the manager and say, hey, don't lower your price because we haven't lowered ours. Then it becomes collusion. If they follow through on my request, then it becomes collusion. Or at least then it becomes illegal. Yeah, then it becomes collusion.
So there's an actual element of trying to change your prices if you illegal collusion, which is what's
There's an element of explicit coordination and communication. Like that's, or at least that tends to be how the law defines it. And again, it's really hard to establish this, but in legal cases, collusion is typically found. Parties are found to be guilty of collusion when there was some kind of communication, some kind of explicit communication. But this is all very gray.
Why exactly is it so illegal? Why does it seem so bad?
Because why do you think it seems to seem
It could make things more efficient.
okay?
In some ways.
Yeah. So, all right. Would you like to?
At the same time, I can also see that if two companies are not actually competing but are collaborating, you could risk getting into a monopoly situation. But at the same time, I would also guess in some situations that
Yeah, I agree. There definitely seem to be situations where,
tariffs, like the American president. I mean, if there's more communication, how prices would be set, there would be less of a chaotic market. And it's
yeah.
things like that.
Well, there's a lot of things in what we're thinking about here, because of course we want companies in a market to coordinate sometimes with each other. We want them to cooperate, right? And that indeed happens a lot as well. But we also want certain kinds of companies to compete with each other. And the reason why we want them to compete with each other is because we expect their competition to to lower price. But the way the price would be lowered is by companies striving to be more efficient in what they do so that they can provide a lower price. And so we expect the presence of a competitor to actually drive this kind of efficiency innovation, which isn't necessarily the kind of technological innovation that we see which invents something completely radically new. That typically requires a lot of exploration, even a lot of wasteful exploration, and you can't really be efficient in that process. But once something is sort of found, once a production process is well defined, we expect the presence of a competitor with a similar production process to lead to this pressure whereby both of us will try to be more and more and more efficient to the point where we are able to provide a lower price. And then we say that's good for consumer welfare. We say that's good for a market because we can buy things for cheaper, things are made more efficiently, all this kind of argument. So, but again, these are all very, economics is messy.
Also throughout the presentation, we're assuming that the customer has a complete knowledge of the whole landscape of the market, in the sense of the price of every single commodity or
Yeah.
quality of every single
Yeah.
which might not be
Absolutely.
true, especially I don't know, also for booking sense maybe also booking could take visibility to show it has two hotels that it wants to make both hotels happy, and booking could show keep the price very high for both and show one hotel to 50% of the users and another hotel.
Yeah. Absolutely. Yeah. Do you think that would make collusion better or worse if consumers don't know these things?
I think it's a different topic other than collusion.
Sure. Yeah. Maybe it's not collusion, but it's yeah.
It kind of infringes a bit on the freedom of the customer to choose whichever product is better, I guess.
Yeah. Yeah, I mean, all these product comparisons on these platforms tend to just be shown to us, and there's an algorithm in the background deciding what we see based on our personal characteristics. So I would say, yes, absolutely, that's...
I think it's kind of obvious based on the questions that this model isn't completely realistic.
Yeah.
Has there been any works that try to match real pricing behaviors in the real world?
So that tends to be empirical work. There's a study that has actually looked quite closely at a period of time. So gasoline companies and that run gas stations shifted, I think in the year 2019, in quite large amount to the use of algorithmic pricing software. And this was documented, I believe, in the US. And so this study looked at the period of their pricing before, actually no, so it's not the US, it was a German gasoline market. And looked at the prices for gasoline that these companies were setting before this period when many were believed to transition to algorithmic pricing, and after. And they found that there was a significant difference in the pricing behavior, and that it seemed like these algorithmic tools did affect gasoline prices. So I think we definitely need to do more investigations of these that look at real-world case scenarios. And on the one hand, one thing that you could do is to really test the algorithms that these companies are using. Of course, that's really hard because we don't know what algorithms they're using. On the other hand, you could just try to study data. You could just try to look at the market and see if you can tell things from that. But then, of course, many other issues come in. We don't know whether companies are using pricing algorithms. We don't know when they might start, when they stopped. We don't have a counterfactual oftentimes. We're not able to compare the period when they did and when they didn't. So, but there are increasingly many studies that show that indeed algorithmic pricing is somewhat of a concern. And the setup that is most frequently looked at is one that is somewhat like this, which is different from what we were studying, right? We studied the very simple Bertrand case where two algorithm designers are competing with each other. But what actually tends to happen is that you have two competitors in a market, which, many more actually, you have many more competitors, and they have a choice between setting their own prices or asking an intermediary platform to set the prices for them, which could be a service provider, like an algorithmic pricing service provider, could be Booking.com. And so that's actually the choice that they often face is, should I set the prices myself, or should I rely on this other third party to set the prices for me, with the knowledge, perhaps, that my competitors may also be using this third-party pricing software. And so then the question becomes, what prices do I get if I set them myself, and what prices do I get if the intermediary sets them for me? And then what kind of outcomes do we see there? And so that tends to be the real-world setting that we have seen mostly today. And in fact, there's quite a lot of active legal cases around this. This kind of collusion is called hub and spokes collusion. So there's this sort of central hub, and then there's many competitors, and they're able to coordinate with each other through the central hub. Yeah, these are the sort of active court cases in the U.S. that are looking at these kinds of things between landlords, between hotels, and so the law is being made as we speak, actually. All right. Well, I think this is now we have come to the end. So if there are any further questions, I will gladly entertain them. But otherwise, I let you go. All right, thank you very much. And I hope you enjoy the rest of the controversies course. Or was this actually the very last lecture? All right.